In this video, we are going to talk more about orthogonal projections, and I say more about it because this is a topic we had started in our last video about orthogonal sets. So this is our overview slide, which we will take about 5 minutes to go over before we go over each topic in more detail and with more examples and proofs. We will start by looking at the orthogonal projection and this problem here. Given a vector y in this drawing, here's my vector y, and a subspace w in Rn. In my drawing, w is the plane here in green. There's a vector y hat in w, this is my y hat vector, such that y hat is the unique vector in w closest to y. So this orthogonal projection, it's basically a line straight down, which is this right angle here, showing it goes straight down to the plane. So y hat is the point closest to y, and y hat is also the unique vector for which y minus y hat, and we'll call that vector z, is orthogonal to w. In other words, we can decompose our vector y into y hat plus a vector that's orthogonal to y hat. So y decomposes into a linear combination of two orthogonal vectors. So these two properties of y hat, first that it's the closest vector in w closest to y, and also the unique vector for which y minus y hat is orthogonal to w, provide the key to finding the least square solutions to linear systems. And this is least square solutions is a topic we will start in this video and cover more completely in our next video. You might feel like this problem is familiar because it's very similar to a problem we had done in the previous video. We were given a vector y, and then we were not given a subspace w, but we were given a vector u, and then we found the projection of y onto u. In this video, we're finding the projection of y onto a subspace w. So the way we find this y hat and also this z, which is equal to y minus y hat, is given to us by the orthogonal decomposition theorem. So let W be a subspace of Rn, then each y in Rn can be rewritten uniquely in the form y equals y hat plus z. So y is a linear combination of this y hat in W and z, which is in W perp. And once we have an orthogonal basis for W, the orthogonal decomposition theorem gives us the formula for y hat. So we compute y hat is equal to y dot u1 over u1 dot u1 times the vector u1 plus y dot u2 over u2 dot u2 times the vector u2 all the way up to y dot up over up dot up times the vector up. And then z is simply y minus y hat. And then we have this example, which we will go over in more detail, but a quick overview is if you have u1 equals 2, 5, negative 1, and u2 is equal to negative 2, 1, 1, and these two vectors span our subspace w. So w is equal to subspace span of u1, u2. Then we have this vector y that's not in w, and y is equal to 1, 2, 3. We want to write y as a sum of a vector in w and a vector orthogonal to w. So we use our formula for the orthogonal decomposition theorem. That was my phone, not yours, sorry. So anyway, using my formula, then y hat is equal to y dot u1 over u1 dot u1 times u1 plus y dot u2 over u2 dot u2 times u2. So starting with the denominator of my first coefficient of u1, I have y dot u1, so y is equal to 1, 2, 3 dot u1 to 5, negative 1 over u1 dot u1 times my vector u1, 2, 5, negative 1, plus then y dot u2, so my y 1, 2, 3 dot u2, negative 2, 1, 1 over u2 dot u2, negative 2, 1, 1 dot negative 2, 1, 1 times my vector u2, negative 2, 1, 1. And we see that vector is equal to negative 2/5 to 1/5. And then that makes z equal y minus y hat. So y is equal to 1, 2, 3 minus our y hat that we had calculated. And then we can decompose y into our vector y hat in w and z in w perp. We will then give a geometric interpretation of this orthogonal projection, which essentially says the orthogonal projection of y hat of y onto w is the sum of projections of y onto one-dimensional subspaces that are orthogonal to each other. So we'll go over that a little more. And then last, we'll look at properties of orthogonal projections, in particular this theorem here, which is the Brest approximation theorem, which gets back to this idea here that y hat is the unique vector in W closest to y. So where is our theorem? Let W be a subspace of Rn and y is any vector in Rn, and y hat be the orthogonal projection of y onto W, then y hat is the closest point in W to y in the sense that the distance between y and y hat is less than the distance between y and v for all other vectors in W distinct from y hat. And last, we have this theorem. If U1, U2 up to UP is an orthonormal basis for a subspace W of Rn, then the projection of y onto W is equal to, and we have a formula to calculate the coefficients in front of the bases vectors. And if U is the matrix then of consisting of the column vectors of the bases, then the projection of y on W is equal to U transpose y for all y in Rn. So there actually are not that many ideas in this video. We have the definition of our problem, the solution and formulas for our problem, and then a little bit of a geometric interpretation which goes quickly, and then also just a confirmation of the second claim that this y hat that we found the formula for here in our theorem is actually the vector in W closest to y. So that's the best approximation theorem. But somehow, with all the proofs and everything, the video is a little bit long, and especially the last example. I'm sorry about that. But anyway, that concludes our overview. So now we can go through all these points in more detail with more examples and some proofs. The first thing I want to do is to compare the problem description we have in this video to the problem description we saw in the previous video, just because it really, when I saw this, I thought, wait, didn't we do this before? So let's just get really clear what we did in the last video and what we're doing in this video, so you don't have that kind of funny sense of what's going on. Anyway, so in this video, we're talking about, we're given a vector y, so here I have it with this blue dot, and a subspace W in Rn, which is this green plane rectangle in Rn, and there's a vector y hat in W, so this vector with this blue dot, which is on the plane, such that y hat is the unique vector in W closest to y. And you kind of get that sense because basically what we do is we take y and we drop a perpendicular vector until we hit W, and that's our y hat. So it's the unique vector closest to y, and y hat is also the unique vector for which y minus y hat, which we're going to call the vector z, is orthogonal to W. And so you see that y then, or this y, is equal to z plus y hat. So y is a linear combination of z and y hat. These two properties, being closest and also unique vector for which y minus y hat is orthogonal to W, provides the key to finding the least squares solutions to linear systems, which we will see this, or we'll introduce that idea later in this video. Comparing that to what we are doing in this video, here in this, in the previous video, we were not given a subspace W, but we were given another vector U in Rn. So this is my vector U here in Rn. I happen to draw it on W, but ignore W for this, because in the previous video we weren't given the subspace W, but we were given U. And what we did is we found the projection of y onto U. So we decomposed a vector y in Rn into a sum of two vectors, one a multiple of U, so we scaled U, and then we added it to another vector orthogonal to U, which was also z equals y minus our y hat being the scaled version of U. Since then our y hat was a scalar multiple of U, our problem then became to find the multiple in front of U. And we used the fact that we were going to decompose y into two vectors, y hat, which was a scalar multiple of U, plus z, which is perpendicular to u. So we use this equation, y equals y hat plus z, where z is equal to y minus y hat, and y hat is equal to a scalar multiple of u. So then we get z is equal to y minus alpha u. And then we looked at this z, and we said it's perpendicular to u if z dot u is equal to 0. So then plugging in y minus alpha u for z, and then dotting it with u, we come up with then y dot u minus u dot u equals 0, which means that our alpha is equal to y dot u divided by u dot u. And then we could say that y hat was our alpha times u. The similarities of these two problems are going to have similar calculations and similar results. So I've cleared stuff out, but I kept my problem description here for this video. We're given a vector y and a subspace w in Rn, and we're looking for y hat in w such that y hat is the unique vector in w closest to y, and y hat is the unique vector for which y minus y hat is orthogonal to w. We often call this vector z. And this is a note we're going to use. So whenever a vector y is written as a linear combination of vectors u1, u2 up to un and Rn, so presumably a basis, the terms in the sum for y can be grouped so that y can be written y plus z1 plus z2, where z1 is a linear combination of some of the u sub I, and z2 is a linear combination of the rest of the u sub I. So I kind of made a little example here. So if we're in R5, if y can be written as a linear combination of u1, u2, u3, u4, u5, then we can group y into a z1 and z2. So I grouped it into a z1 and z2, where z1 is a linear combination of some of the ui. In this case, I chose z1 to be in the span of u1 and u2, so it's a linear combination of u1, u2, and then z2 is a linear combination of the remaining ui. So it's a linear combination of u3, u4, u5. In other words, z2 is in the span of u3, u4, u5. So this is written out like this, it seems obvious, but this is the note we're going to use. And I also wanted to remind you that W perp, which we denote this way, W perpendicular with the perpendicular sign, denotes the set of all vectors orthogonal to a subspace W. We had discussed this in the last video, but here's your reminder. This next example here will give us the ideas to find the formula for y hat, as well as a proof that y can be decomposed into our y hat and our vector z, which is equal to y minus y hat, which is orthogonal to w. So the first step comes directly from this note we had discussed. So we have y as a linear combination of our bases vectors, and we can divide it up into z1, which is the span of u1, u2, and the rest as a vector z2, which is in the span of u3, u4, and u5. But the additional thing we want to do is write y as the sum of a vector z1 and w, which we have done, but we also want to verify that our z2 vector is in y perp. Which is why I reminded you this definition of y perp denotes the set of all vectors orthogonal to a subspace W. So we want our z2 to be orthogonal to z1, which is the span of u1, u2. So then looking at this definition to show z2 is in W perp, right? It is sufficient to show that z2 is orthogonal to a basis for W, right? Because W perp is a set of all vectors orthogonal to W in this case. So we want to show that z2 is orthogonal. Our basis then is going to be u1 and u2. So now I'm going to take z2 and dot it with u1. So z2 I have here. It's our linear combination of u3, u4, and u5 dotted with u1. So by the dot product, I can distribute that. So I get c3 u3 dot u1, c4 u4 dot u1, and c5 u5 dot u1. But now, because u1 to u5 is an orthogonal basis, that means my u1 dot u3, u1 dot u3 is going to 0. And u4 dot u1 also goes to 0, and u5 dot u1 is 0. Again, because this is an orthogonal basis. So similarly, I can show that z2.u2 is equal to 0, and therefore z2 is in W perp. And that finishes this first example here. Now we are ready to use those ideas from the last example to solve our orthogonal projection problem here. And with that, the solution is in the orthogonal decomposition theorem, which says let W be a subspace of Rn, then each y in Rn can be written uniquely in the form y equals y hat plus z, where y hat is in W, our subspace, and z is in W perp. In fact, if u1, u2, up is any orthogonal basis of W, then we can write y hat as a linear combination of that orthogonal basis, and we have this formula here for each of our coefficients, which is essentially y dot u sub I over u sub I dot u sub I times the vector u sub I for I equal 1 to p. And then z is equal to y minus y hat. And just a quick note before we prove this theorem, in our previous work, we were using an orthogonal basis for Rn, but this decomposition theorem here only requires an orthogonal basis of W, and that's this note here. The theorem tells us that decomposition of y into z1 and z2, where z1 is in W and z2 is in W perp, can be computed without having an orthogonal basis for Rn. It's enough to have an orthogonal basis only for W. And now we are ready to work on the proof. So we are given that we have a subspace W of Rn, and we have an orthogonal basis for W. And we want to show that for y, we can write that uniquely in the form of y hat plus z, where we're given this formula for y hat and this formula for z. So we're going to show that this formula for y hat is in W, and this formula for z is in W perp. We are going to start by showing that this formula for y hat gives us y hat in W. So we're given our orthogonal basis for W and y hat. We have that formula here, and we also have z is equal to y minus y hat. Well, y hat is in W. That's pretty straightforward because y is a linear combination of the basis vectors of W. So this part, that works out fairly easily and straightforward. The next part of our proof is to show that z equals y minus y hat is in W perp, because by doing this, we've shown if z is equal to y minus y hat, that means y is equal to z plus y hat over here. Y is equal to z plus y hat. And we have shown then that y hat is in W and z is in W perp. And so we have found our decomposition of y into y hat plus z. So again, we need to show that z is equal to y minus y hat is in fact in W perp. But again, to show something is in W perp, we need to show that z is perpendicular to a basis for W. So here I start by taking z dotted with u1. So z is equal to y minus y hat dotted with u1. So distributing the u1, I have y dot u1, and then I have y hat, which I copied my formula here, dotted with u1. Distributing then my u1 inside this into y hat, so I still have my y minus dotted with u1. Then I have y dotted with u1 over u1 dot u1 times u1 dotted with this u1 here. I have my y dot u2, u2 dot u2 times u2 dotted with this u1 here, up to y dot up, up dot up times up dotted with this u1. Now, because u1 up to up is an orthogonal basis, these all go to 0. The u2 dot u1, everything in between up up to u1, this all goes to 0. Here, what you can see is I can group these two together, and I have my u1 dot u1 over u1 dot u1, so this is just equal to 1, so I have y dot u1 minus y dot u1, which is equal to 0. So since the dot product of z and u1 equals 0, that implies that z is perpendicular to u1. Similarly, I can show that z is perpendicular to all the basis vectors for W, and therefore z is in W perp. So what I have shown is we can take any vector y in Rn and we can decompose it into two vectors, a y hat that is in a subspace W and a z that is in W perp. And I have given the formulas for this decomposition and have proven it satisfies this theorem here. Actually, I spoke a little too quickly because this theorem also says that this y hat and this z are unique, but I'm going to leave you to look at the book for the proof of uniqueness. And now we are ready to do our first example of the orthogonal decomposition theorem. So let u1 equal to the vector 2, 5, negative 1, and u2 equal to the vector negative 2, 1, 1, and y equal to the vector 1, 2, 3. We can observe that u1, u2 is an orthogonal basis for the span of u1, u2. Then the problem is to write y as a sum of a vector in W and a vector orthogonal to W. So the first thing I did is I wanted to observe that u1, u2 is an orthogonal basis for the span of u1, u2. So, of course, to be a basis, you need to both span and also be linearly independent. But if they are orthogonal, they're linearly independent. So all I need to do really is to show that u1 is orthogonal to u2. So I do that. So u1 is perpendicular to u2 by taking the dot product of 2, 5, negative 1 dot negative 2, 1, 1. And this gives me my negative 4, 5, minus 1. That gives me 0. Next, I'm going to use my formula here for y hat, which is y dot u1 over u1 dot u1 times u1 plus y dot u2 over u2 dot u2 times u2. So y dot u1, so here I have my vector y, 1, 2, 3, dot my vector u1, 2, 5, 1 over 2, 5, 1, negative 1, sorry, dot 2, 5, negative 1 times my u1 vector, 2, 5, negative 1. And for whatever reason, I decided to do my dot product in this kind of vector calculus look. But anyway, now I have my y dot u2, so y is 1, 2, 3, dot u2 is negative 2, 1, 1, divided by u2 dot u2, so negative 2, 1, 1, dotted with negative 2, 1, 1, times my vector u2, negative 2, 1, 1. So my vector for y hat is going to be equal to negative 2/5 to 1/5. Next, I'm going to calculate my vector z, which is just y minus y hat. So my y is 1, 2, 3 minus y hat, which is negative 2/5 to 1/5. So z is equal to 7/5, 0, and 14/5. So I can then verify. Now my vector y, which is equal to 1, 2, 3, is equal to my y hat, negative 2/5 to 1/5, plus 7/5, 0, 1/5. And first, we want to verify y hat. Well, it is a linear combination of u1, u2. So we do have y hat in W, and then we have this calculation for z, and we can also verify that z is perpendicular to u1 and u2, which I have here. Z dot u1 is 7/5, 0, 14/5 dot. My u1 is 2, negative 5, negative 1, and that's equal to 0. And then z dot u2, here's my z. My u2 is negative 2, 1, 1. That's also equal to 0. So again, I've decomposed my y into a vector y hat that is in the span of u1, u2, and also in plus z, which is in the W perp. There is a geometric interpretation of the orthogonal projection. So the orthogonal projection y hat of y onto W is the sum of projections of y onto the one-dimensional subspaces that are orthogonal to each other. The picture that goes with this geometric interpretation is right here. So here at this top, I should make this blue, this dot blue. This is my vector y. And then over here, I have my vector u2 and my vector u1, which defines a subspace in this picture of R3. So here's my y in R3, here's my u1, u2. I take the projection of this y onto W, and I'm going to use this definition here, or this kind of claim here, which I have not proven, but we will do that in this video, that this y hat is the vector in W closest to y. So to find the y hat in this picture, we're just going to drop a line perpendicularly down from y down to W, and this is our y hat. And what this orthogonal projection says, that this y hat is the sum of projections of y onto one-dimensional subspaces that are orthogonal to each other. So in other words, if I project y down to this, and this kind of looks funny. So this is my coordinate, but if I project y then down to u2, I'm going to get this y2 hat. So this is the projection of y on my u2 axis of W, or my basis of W. And then here, this is my projection of y down to y1. Now, why doesn't it look like this point here? You know, it's because of the way we have to draw, let's see, a three-dimensional space using a two-dimensional piece of paper. But right, so if I took then this and this dimensionally, right, this vector here is going to be the sum of this y2 and y1 to give me y hat. And this geometric interpretation, I'm going to compare that to the geometric interpretation we had in our last video when we found coordinates of an orthogonal basis. Remember, if we had a vector y and then we wrote y as a linear combination of an orthogonal basis, we could find each of these weights for each basis vector because they were orthogonal. So when we dotted with y with u1, all of this would go away and we'd be left with y dot u1 is equal to c1 u1 dot u1, which meant c1 is equal to y dot u1 over u1 dot u1. So anyway, in our last video, we talked about this geometric interpretation of this theorem for finding coordinates of orthogonal bases. And we said the geometric interpretation was that the theorem decomposes y into a sum of orthogonal projections, right? This is some scalar multiple of u1 plus a scalar multiple of u2. And so this is how this theorem is very analogous to this one. And that here we have y hat is the sum of orthogonal projections of y onto all these different bases, right? So y hat is some scalar multiple of our u1 up to, and then a bunch of scalar multiples of our bases vectors. So these are very, even the formulas, right? They're analogous, totally analogous. Okay, now we're ready to look at properties of orthogonal projections. In particular, so we've had this theorem that told us to find how to find this y hat and z of our original problem, but I haven't talked about this claim here, that y hat is the unique vector in W closest to y. So that's exactly what we have here. It's the best approximation theorem. So let W be a space of Rn and y be any vector in Rn, and y hat be the orthogonal projection of y onto W. Then y hat is the closest point in W to y, in the sense that y, the length or the magnitude, the difference between y minus y hat is less than the difference between y minus v for all other v and w. So all v and w distinct from y hat. And we have one more theorem here, but before we get to it, let's take a closer look at the best approximation theorem. I have my orthogonal decomposition theorem here, which gives us our formula for y hat and z. And then I have my best approximation theorem, which makes the claim that y hat is the point in W closest to y. We are going to start with a vector v not equal to y hat. And here's our picture. Here's our y and our y hat, which is just found by dropping a perpendicular down onto W. And here's another arbitrary vector v, also in W. And what we want to show is the distance between y and y hat is less than y and v. And again, v is arbitrarily chosen. So, but it's chosen such that it is not equal to y hat. And since since v and y hat are in W, then we'll also consider the fact that y hat minus v, that's this vector here, the distance between y hat and v, is also in W. So this vector y hat minus v is in W. By the orthogonal decomposition theorem, y minus y hat, which is z, y minus y hat here, is orthogonal to W. In particular, y minus y hat is perpendicular to y hat minus v, because y hat minus v is in W. So far, I've looked at y minus y hat here, and I said it's perpendicular to y hat minus v. But I need to start considering y minus v over here, because that's, what we're trying to prove, that y minus y hat is less than y minus v. So I'm going to introduce my y minus v, but I want to relate it to these other two vectors that I have, because it forms this triangle, right? And this is perpendicular, so I can use the Pythagorean theorem. So my y minus v, I'm going to break that up into, I'm going to introduce in between this y and v a minus y hat and a plus y hat. So y minus v is equal to y minus y hat plus y hat minus v. So you can see this is algebraically equivalent. And as I said, now we can use the Pythagorean theorem. So we have y minus v squared, that's our hypotenuse, is equal to y minus y hat squared plus y minus v squared. And now, because y hat does not equal to v, this value here, where is it, y hat minus v, is greater than 0, which tells us that our y minus v squared is less than y minus y hat, is greater than y minus y hat squared. And since it's true, the square, when we take the square root, this here is true, and we have finished our proof. Our next example is given vectors u1 equals 2, 5, negative 1, the vector u2 is equal to negative 2, 1, 1, and the vector y is equal to 1, 2, 3, and w is the span of u1 and u2. Find the closest point in w to y. By our best approximation theorem, y hat is equal to y dot u1 over u1 dot u1 times u1 plus y dot u2 over u2 dot u2 times u2, and this is the closest point. So here I have y dot u1, the first part, the numerator of y hat is our y is equal to 1, 2, 3 dot u1 is equal to 2, 5, negative 1 is equal to 9. u1 dot u1, and I just decided to use it in this form because it's less space consuming. So I have 2, 5, negative 1, 2, 5, negative 1, and that's equal to 30. Then I figured out the numerator of the second of the coefficient of u2. So y dot u2, here I have y, 1, 2, 3 dot u2, negative 2, 1, 1 is equal to 3, and u2 dot u2, so it's negative 2, 1, 1 dot negative 2, 1, 1 is equal to 6. So my y hat is equal to my first coefficient, which is 9 over 30 times u1, which is 2, 5, negative 1, plus my next coefficient, so that's going to be 3 over 6 times u2, which is negative 2, 1, 1, which is equal to negative 2/5, 2 and 1/5. Our next example, the distance from a point y in Rn to a subspace W is defined as the distance from y to the nearest point in W. So find the distance from y to W equals the span of u1, u2, where the vector y is equal to negative 1, negative 5, 10, and u1 is equal to 5, negative 2, 1, and u2 is equal to 1, 2, negative 1. By our best approximation theorem, the vector y hat in W that is closest to y is equal to y dot u1 over u1 dot u1 times u1 plus y dot u2 over u2 dot u2 times u2. So this is the closest point in W to y. Plugging into this formula, I'll start with the y dot u1 is equal to, where's y? Negative 1, negative 5, 10 dot u1, which is 5, negative 2, 1, is equal to, looks like 10 plus 10 is 20, minus 5 is 15. u1 dot u1 is our 5, negative 2, 1 dot 5, negative 2, 1 is 30. Doing our denominator of our second coefficient of u2, our coefficient of u2 is y dot u2, which is negative 1, negative 5, 10 dot u2 is 1, 2, negative 1, which is negative 21. u2 dot u2, so we have our 1, 2, negative 1 dot 1, 2, negative 1 is equal to 6. So our y hat then is equal to our first coefficient, which is our 15 over 30 times u1, which is 5, negative 2, 1, minus our second coefficient, which is negative 21 over 6 times u2, which is 1, 2, negative 1, which is equal to negative 1, 8, 4. So this is the point in W closest to Y. So we want to find the distance from Y to W. So now we need to find the distance of Y hat. That's the point in W closest to Y. So the distance from Y hat to Y. So Y minus Y hat, I have Y is equal to negative 1, negative 5, 10 minus Y hat, which we just found, negative 1, 8, 4 is equal to 0, 3, 6. We can find the magnitude or the distance from Y minus Y hat is the square root of 0 squared, 3 squared, 6 squared. So the distance is equal to 3 square root of 5. From this last example where we define the distance from a point to a subspace as the distance from our point Y to the nearest point in W, we'll later see that sometimes when we cannot calculate Y for whatever reason, that we can approximate Y with a vector V, and the distance from Y to V will be regarded as the error of using V in place of Y, and this error is minimized when V is equal to Y hat. Last we have this theorem. So if we have U1, U2 up to UP is an orthonormal basis for a subspace W of Rn, then the projection of Y onto W is equal to this formula here. Y dot U1 times U1 plus Y dot U2 times U2 up to Y dot UP times UP, which gives us, if U then is the matrix with column vectors U1, U2 up to UP, then the projection of Y onto W is equal to U transpose Y for all Y in Rn. I have this theorem written here, and we will do the proof. So first, the projection of Y onto W from our orthogonal decomposition theorem is this formula here. Y is equal to Y dot U1 over U1 dot U1 times U1 all the way up to Y dot UP over UP dot UP times UP. And we also have this formula here for Z is equal to Y minus Y hat. I'm sure you're tired of hearing me say this formula. But anyway, because here in this theorem, we have an orthonormal basis, we can simplify this a little bit, because if it's orthonormal, that means Ui dot Ui is equal to 1. So we can kind of say that this is just divided by 1. So we could say Y hat is equal to Y dot U1 times U1 up to Y dot UP times UP. So again, this is what Y hat looks like according to the orthogonal decomposition theorem. From here, we want to show that if we take U equal to this matrix here, then this Y hat, which is the projection of Y onto W, is also equal to U transpose Y. So what we've shown from this decomposition theorem that Y hat is a linear combination of our U1 up to UP of our orthonormal bases, which are the column vectors of U. So now I'm going to verify this formula here that Y hat is equal to U transpose Y. And I say Y hat because Y hat is the projection of Y onto W. So let's look at U transpose Y. So U is our column vectors U1, U2, UP. Our orthonormal bases are our column vectors. And then U transpose, this first row then is U1. So the first indice tells me what basis vector it is from, and the second indice tells me what coordinate it is in that basis vector. Here's my U2 written transposed and my UP transposed. Here's my vector Y. So what I have is my matrix U, and then my U transpose times Y essentially is equal to my U1 dotted with Y, U2 dotted with Y, up to UP dotted with Y. So then when I multiply then by U, I'm going to get U1 times U1 dotted with Y, U2 times U2 dotted with Y, up to UP dotted with Y. This should be a P here, not an N. So you can see now this formula here that I got with my matrix is the same thing as the formula I got with the decomposition theorem, which verifies that now I can calculate my y hat, or my projection of y onto W, using this matrix here. This next example is a pattern recognition problem or application. So if you have a grid of 9 by 9 kind of squares, and then you color some of them in, you want to be able to recognize the patterns. So let W be a vector generated from a pattern of blue and white squares by turning each blue square into a 1 and each white square into a 0, and then lining up each column below the column before it. So here our first column, we have white, white, blue, so that's going to be 0, 0, 1. Our second column is blue, 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 so that's going to be 1, 1, 1. And our last column is white, white, blue, so that's 0, 0, 1. Again, 0 for white, 1 for blue. So now we're going to line up these columns. So 0, 0, 1 is our first part of our vector W, 0, 0, 1. Our second column is 1, 1, 1, so that's the next part of our W, 1, 1, 1, or our vector W. And then last we have 0, 0, 1. So our last part of our column vector W is 0, 0, 1. And the idea of this pattern recognition is we can have other patterns of blue and white squares, and we code it into a vector. Then all of these vectors, we want to be able to multiply it by a matrix and then tell us whether or not we have the pattern that we're looking for. In this example, we're going to look for this pattern. So the idea is if we want to recognize this symbol here, which your book is calling the perp symbol because it looks like W perp, the perpendicular symbol. So if we want to recognize this pattern here, we create W, our vector generated using these instructions, and we let our subspace capital W equal to the span of this vector W. Then we're going to choose a basis, V1, V2 up to Vn, for W perp. And from this basis, we're going to create a matrix B, which is our basis vectors, the transpose used as our rows of W perp. So this is our matrix B. Then we're going to note if we have another vector U that represents some other pattern, or possibly the same pattern, but it represents a pattern of these blue and white squares, when we multiply it by B, it's going to be equal to 0 if and only if U is perpendicular to a set of basis vectors for W perp, because that's how we made B. So if and only if U is in W. Okay, so again, we have W, we make a basis that's perpendicular to W, and then we create a matrix from that, and then when we want to test if our pattern is equal to this perpendicular pattern, we multiply times B, and it's only going to be equal to 0 if U is perpendicular to W perp, which means it is actually in the span of W. There is this proof here, which I'm not going to go through, but just to kind of verify what I just said, that the B times U equals 0 implies that U is in W, that is, that it is in the span of W, the vector W. And actually, there is one other point. There is the possibility that U is equal to 0, so 0, W is equal to 0. But U transpose M, U is equal to 0, but U transpose U is not equal to 0, implies that U equals W. So we're going to illustrate these ideas with an example now. So we're going to actually find that matrix M to recognize this perp symbol here. So I'm going to start here. I'm going to let W equal to the span of W. I have my vector W here, so W transpose is equal to 0, 0, 1, 0, 0, 1, and then 1, 1, 1, our 1, 1, 1, and our 0, 0, 1, 0, 0, 1. And W is equal to the span of this vector W. Next, I need to choose a basis for W perp. To find a basis for W perp, first I want to find an x dot W equal to 0. So here we have an n-dimensional vector. So I have x1, x2 up to x9 dotted with my W 0, 0, 1, 1, 1, 1, 0, 0, 1 is equal to, well, this is 0. My x2 is 0. So my x3, x4, x5, and x6 are in my are non-zero, and then x9 is non-zero. You can see, right, that 0 times x1, 0 times x2, 1 times x3, 1 times x4, 1 times x5, 1 times x6, 0 times x7, 0 times x8, and 1 times x9. So that's what our dot product here gives us. x3, x4, x5, x6, x9 added together equals 0 when we're trying to find x dot W equals 0. So that means if we let x4, x5, x6, and x9 be free variables, the x3 has to equal to negative x4 minus x5 minus x6 minus x9. So all other x of i's are free. So just to be really explicit to show you what this looks like, this is what our vector x looks like. We have x1, x2, x4, x5, x6, x7, x8, and x9 are free. And then the only condition we have is that x3 plus x4, x5, x6, x9 is equal to 0. So in other words, x3 is equal to minus x4, minus x5, minus x6, minus x9. Now, if I want to make a basis for vectors of this form, this is something you've done numerous times before. I don't know why it seems to be so much more complicated. I guess because there's just so many rows and columns, but it's something you've done before. So I've broken this up into 1, 2, 3, 4, 5, 6, 7, 8 vectors. And you can verify if you multiply x1 times its first vector, add that times x2 times its second vector, this times the third, you will get exactly this vector here. So I have now my bases, 1, 2, 3, 4, 5, 6, 7, 8. 8 vectors for my basis vector for W perp. And remember, because I got this vector by dotting x dot W and setting it equal to 0. And now I'm going to use this basis for W perp to create my matrix here, B. So I copied my basis up here, and then I made my matrix B from these columns here. And remember, it's transposed. So my first basis vector has a 1 in the first position. My second basis vector has a 1 in the second position. My next basis vector has a negative 1 in the third position and a 1 in the fourth position. So that's this. This is x4. You can verify this is x5 transpose, this is x6 transpose, x7 transpose, x8, and x9. I labeled them. And now our matrix M is equal to B transpose B. So I did that multiplication, and you'll have to take my word for it, or you can verify it, that this is B transpose B. So what you want to notice is now this is our matrix to recognize this symbol here. And what you'll notice is if you take W transpose times this matrix times W, it'll equal to 0. Any other pattern will not equal to 0. Oh, I should say except possibly the 0 vector. W is equal to 0. But the other thing to eliminate the fact that maybe W is equal to 0 as opposed to this pattern here, 0 being all white, is that if you also take W transpose by times W, it will not equal to 0. So this is this is the matrix along with this one other calculation. You can confirm that what you have is the pattern of the perp symbol. So, and just to use this as an example, let's say you have this symbol here, which is translates to 1, 0, 1. That's our first column. Our next column is 1, 1, 1. So that's our next column, and then our last column is 1, 0, 1 over here. When you take this vector w, multiply it by m, and then multiply by w, you're going to get 2. So that means it's not the perp symbol. Only if it's equal to 0 is it the perp symbol. And also, well, you don't actually have to do this calculation at this point. But now when you do the perp symbol, take this vector, multiply it w transpose mw, you'll get 0. And again, to distinguish, to make sure that w is not simply the 0 vector, you also do the calculation w transpose times w is equal to 5. So this 0 here, and the fact that this is non-zero, tells you that the pattern you have is indeed the perp symbol. Now we've covered all the material in our video. I do have a couple of more problems for you, but I'm going to suggest before you look at the solution, you pause the videos and give the problems a try. The first problem is to use the fact that u1 and u2 are orthogonal to compute the projection of y on w, where u1 is equal to -7, 1, 4, u2 is equal to -1, 1, -2, and y is equal to -9, 1, 6, and w is equal to the span of u1 and u2. The second problem is let w be a subspace of Rn, and let x and y be vectors in Rn, and let z equal to x plus y. If u is the projection of x onto w, and v is the projection of y onto w, show that u plus v is the projection of z onto w. So this problem here, where we're computing the projection of y onto w, where w was the span of -7, 1, 4, and -1, 1, -2, and y is equal to -9, 1, 6, I used this formula here from the orthogonal decomposition theorem. I'll let you look at the math because it's fairly straightforward, but the answer should be -9, 1, 6. The next problem is if w is a subspace of Rn, x and y are vectors in Rn, and z is equal to x plus y. If u is the projection of x onto w and v is the projection of y onto w, show that u plus v is the projection of z onto w. So I started with an orthonormal basis for w, and then our matrix U is equal to the matrix with column vectors made from our orthonormal basis. And then I use this theorem here, that if U1 up to UP is an orthonormal basis W for Rn, then the projection of Y onto W is equal to this formula here, which we can also use the matrix U transpose Y. So now the projection of Z onto W is equal to U transpose Z, but Z is equal to X plus Y, and by, properties of matrix multiplication, because it's linear, is U transpose X plus U transpose Y. This is the projection of X on W. This is the projection of Y on W. And that's exactly what I wanted to prove. To summarize what we have covered in this video, we have looked at orthogonal projections. So the problem we were looking at is given a vector y in a subspace W and Rn. There's a vector y hat in W such that y hat is the unique vector in W closest to y, and 2, y hat is the unique vector for which y minus y hat, we called that vector z, by the way, is orthogonal to W. And we have this orthogonal decomposition theorem, which told us how to calculate y hat, and also z, which is just equal to y minus y hat. But the orthogonal decomposition theorem said let W be a subspace of Rn, then each y in Rn can be written uniquely in the form y equals y hat plus z, where y hat is in W and z is in W perp. And in fact, if we have this orthogonal basis for W, then we can find y hat using this formula here, which is y dot u1 over u1 dot u1 times u1 plus y dot u2 over u2 dot u2 times u2, all the way up to y dot up over up dot up times up. And then, of course, z is equal to y minus y hat. And we had this first example here. So if we have w is equal to the span of u1 and u2, where u1 is equal to 2, 5, minus 1, and u2 is the vector minus 2, 1, 1, and we have our vector y not on w is equal to 1, 2, 3, we can write y as a sum of a vector in w and a vector orthogonal to W. So we use this, straightforwardly use this formula from the orthogonal decomposition theorem to find y hat, and that's the vector in W. And then y hat was equal to this vector here. And then we found z by using this formula here is y minus y hat. There was this geometric interpretation of the orthogonal projection. So the orthogonal projection y hat of y onto W is the sum of projections of y onto the one-dimensional subspaces that are orthogonal to each other. The one-dimensional subspaces are the ones given to you by your orthogonal bases. Last, we have properties of orthogonal projections. The first one is this theorem here, the best approximation theorem, that gave us this fact here, that y hat that we calculated using this orthogonal decomposition theorem is the unique vector in W closest to y. So I'll just read the best approximation theorem. Let W be a subspace of Rn, and y is any vector in Rn, and y hat is the orthogonal projection of y onto W. Then y hat is the closest point in W to y, in the sense that the distance between y minus y hat is less than the distance between y minus any other vector v in W. Last, we had this theorem: if we have u1, u2 up to up an orthonormal basis for a subspace W of Rn, then the projection of y onto W, given the same one given to us by the orthogonal decomposition theorem, can also be calculated using this matrix U, which is composed of the orthonormal bases as column vectors. Then the projection of y onto W is equal to u transpose y. And that's it for this video. Thank you for watching.